Friday, February 16th, Season 2, Episode 7, Mind Body Evolution. Hi, Josh.
Hi, Eric. So, today...
Closing the door. I normally do that before we start.
Today, I would like to talk about something further afield again. I talked about sugar last time. I gave everyone a pure discussion on health-related matters, just biology. But I kind of have a hobby where I like to look at other fields and see what look like discrepancies or things that don't necessarily fit perfectly within their sort of concept of themselves. And one of the things I've been interested in for a very long time is cosmology. And there were ideas that I actually came up with as an undergraduate that I've only begun to understand are not what everyone thinks. And so I thought I would be interesting to sort of juxtapose how I see the universe as working and how Google says the universe works.
Okay.
And we disagree. And I think I'm right. So it'll be interesting, and I think it'll be interesting to see my reasoning to see why I say Google is wrong. And I think Google has to be wrong for a very simple reason, that the universe is the universe as we know it everywhere. I could be wrong about this.
Wait. Google says something different than that?
Yeah, we'll get there.
Okay.
But we're gonna talk. So.
That the universe is the universe everywhere you look. You're saying it's the same everywhere.
Yes.
That the principles that apply here
apply everywhere else.
As far as you can go.
So people have been thinking about this for a very long time. You had the Pythagoreans, you had the Neoplatonists, you had people trying to reconcile Greek cosmology with Egyptian cosmology. We've talked about that. There's been a lot of talk about what the universe is, this sort of undivided whole from which many things then come. And this has been a through line in human understanding for a very long time. It probably predates writing. The idea that there was nothing and then there was something, because it has to kind of be like that.
Right. Otherwise, there was something all the time, or how does that work?
That's another possibility, but infinities get hard to think about.
Right.
And so...
so does nothing.
Yeah, so does nothing. And so all of these things are problems. And they've been problems for philosophers for a long time. One of my favorite philosophers was Parmenides. He was a pre-Socratic philosopher, and he said, don't let anyone ever tell you that not being is. And I really liked that. Mm-hmm. It was part of why they had a hard time with zeros, because zero is a circle around nothing, which then takes that nothing and says it's right there, which is hard to talk about, because how can nothing be a place?
How can you localize nothing?
Yeah, exactly. But that's what a zero is. There's lots of interesting ideas about it. Indian concepts of zero is negative infinity plus positive infinity equals zero. It's not a circle around a something. It's all of everything, and is a zero.
Nothing.
And nothing, exactly. And I actually think that this represents the universe pretty well, which we'll be getting into eventually. The universe is a big giant zero, which is interesting to think about. It's
not a pot of milk.
But this is also a hypothesis. No, it's not a pot of milk. The Milky Way, though, is interesting. The idea of a galaxy is literally milk. Galactose, it means milk. Mm-hmm. Swirling. It's when you pour cream into your coffee. That's exactly what the Greeks were thinking about when they thought about a galaxy. That swirly, spirally shape.
I can go for that.
Yeah, exactly. So in early Greek thought, you had the idea of this undivided one, of which there is nothing that isn't that one. That would be what Parmenides would say. There's nothing that's not the universe, because it's the universe by definition. And
you can't get outside of it to where there's nothing.
Because it's the universe.
Right.
There is no nothing outside the universe. There is no nothing.
There's no outside.
There's no outside. Universe. There's just the universe. Yeah. And so that's the one of Parmenides. And he talked about it being bounded by ligatures of strong necessity. The idea of...
That's a beautifully vague way of speaking.
So it was bound by what needs to be. There can't be a thing that isn't that because it's what needs to be. And they literally envisioned it as an egg wrapped around with snakes. And those were the ligatures of strong necessity. Chronos and Ananke, time and necessity, were what binds the universe together. You can't escape either of these things. What is necessary is necessary.
Sounds like a tautology.
Well, it is. The universe is a tautology. And you can't escape it. That's the whole point.
That's the point.
That is the point. So this had been going on for some time in a sort of philosophical way, and people had different concepts. Maybe the universe was infinite from the beginning. There was no beginning. It was just infinite. Or maybe there was a beginning and it started somewhere. And so this was a major change as Christianity starts, because in Christian thought, there is a beginning to the universe. And in Jewish Old Testament thought, there's a beginning to the universe. This is a concept that was then sort of being reconciled with these Greek cosmologies, some of which were infinite in all directions, other ones were infinite in different ways, but there would be bounded infinites, different ways to think about infinity, and that there's nothing outside this infinity. And these in the Middle Ages were then being sort of trying to reconcile ideas of Greek and Egyptian thought and coming up with ways to talk about it that were bringing all of these together. And this was the origin of alchemy. So the first, truly medieval alchemical text was something called the Emerald Tablet. And the Emerald Tablet was supposedly written in Greek by Hermes Trismegistos, so a combination of the god Hermes and Thoth Trismegistos. So Thoth is the scribe of the Egyptian world, the ibis-headed god, and he combined with Hermes carrying the caduceus with the wings on his ankles and became this author who wrote a book called the Emerald Tablet. And the Emerald Tablet has become the sort of text of all alchemy and magical thinking. And one of its primary things, the thing it really that people take away from it is the saying, as above, so below. That what is in the heavens is what is on earth, and what is on earth is what is in the heavens.
So you're saying that, pardon me, you're saying that that's one of the oldest concepts.
It's one of the concepts that has been a through line. There's versions of it in basically all texts. So when you say something like God created man in his image, that would be an example of that. Mm-hmm. That would be as above, so below. That everything's the same in all directions conceptually, because the microcosm represents the macrocosm, and the macrocosm can be found in the microcosm.
This is the way things need to be.
This is the way things need to be. That everything is fractal at all scales and all the way up and all the way down. This again.
I'm sorry, I can't help but think about the turtles again.
Yeah, exactly. It's fractal turtles in all directions. But you can imagine fractal turtles would get smaller and smaller as they go out. You'd still have finite turtles. If you had, fractal turtles each standing on a smaller turtle as they went, you could end up with a bounded batch of turtles. You'd have a Mandelbrot turtles, essentially. You would have something that had limited size but infinite turtles.
Is the Mandelbrot, is that bounded? Or
it is. Mandelbrot has a particular...
zooming in on it. It ends?
It doesn't end as when you zoom in, because it gets smaller and smaller. But the size of the Mandelbrot set as a whole giant concept is one thing, and has a particular finite size.
You can conceptualize the thing that creates something that.
Right. So if you had a turtle standing on 4 smaller turtles, and each one of those smaller turtles was standing on 4 smaller turtles, you could have, as an entire set, you could have something of finite size with an infinite number of turtles, because the smallest turtles would be infinitely small.
Right.
It's angels dancing on the head of a pin.
Yes.
Yeah. These are all the concepts that humans have been dealing with for a long time. We make fun of them in many ways because these things do seem a little bit bizarre when you take them to their logical extremes, turtles all the way down. Duns Scotus was this medieval philosopher who was talking about hierarchies and the arrangement of the world. And he's one of the ones who was coming up with how many angels could you arrange in a hierarchy. Yeah. And so we get the idea of a dunce cap from him, from the philosopher Duns Scotus, and we put on a medieval coned cap looking like a witch or a wizard, and we sit in the corner as Duns Scotus.
Because his ideas were
so mocked by the Age of Reason, by the time you get to the 18th century, that he was the example of someone who was an idiot.
I had no idea where that came from.
Yeah, and we get the word idiot from a private person. Idiota means literally idiosyncratic, someone who's an individual, someone who's not part of the society and is different from them.
Wonderful.
So anyway, these are interesting ways we've mocked people over the years. Is their cosmologies, and they're separating out from everyone because they see something different, and that would definitely make me among their crew. I feel like this a lot. So anyway, the idea in the Emerald Tablet of as above, so below was really important for Newton. He made his own translation of the Emerald Tablet. He was an alchemist, and it was how he understood the universe. So when he was trying to understand gravity, gravity had to be the same everywhere. Gravity had to work the same at all levels. So it had to be the way the solar system held together, and it had to be the way that a rock was attracted to the earth. All of these things had to be in common. They had to be a direct relationship between, say, gravity and mass. There's no reason that there is one. It's almost a alchemical concept that the heavier something is, the more mass it has. And so it's exactly equal. So a marble and a bowling ball fall at the same rate. Why is that? A bowling ball is being pulled down more than the marble. Why is it not moving faster? It's not moving faster because its inertia slows it down at exactly the same amount as it's being pulled by its mass. So the inertia made by the mass is exactly proportional to the gravity made by the mass. And so there's these beautiful sort of symmetries that Newton was seeing as an alchemist that informed his mathematics and informed the way he was trying to conceptualize the world. That all of these things had to be true and had to be these sort of unifying ideas. That you can then express these in math, which was he saw as the pure alchemical language, the language which you could not lie in. Because the things you described had to be the way they were described. They couldn't be a different way. And
because if they were a different way, the equation wouldn't work.
And so this is how he was viewing the world, but it was coming from what had been magical thinking, that everything has to be the same, that the microcosm has to be the macrocosm. And he was then expanding this to say, if the universe truly works this way, then I can say things about the universe by looking at the microcosm. I can run experiments. And so he was creating modern experimental physics as an alchemist. And so he was doing microcosm experiments to understand a cosmology, a mythology, a spiritual world that he was understanding as a way the world had to be. Because it doesn't have to be that way. Things could be different at different levels. You know, I was mentioning before we started that this was why Einstein really hated quantum mechanics. You know, he said, "I don't like the idea that God plays dice with the universe." But what he really, really hated was the idea that at some scale the universe was different from what we see, and that we tend to still think of it as the microcosm is the macrocosm. You know, we want to think of atoms as little planets surrounding a sun.
We want to think of things as things that we can actually think of.
Right. And clearly atoms are not that. And the quantum world is different from the larger world.
How do we conceive of that? How do we talk about it?
So this idea breaks down at certain levels, and it's not supposed to. As an alchemical idea, it's supposed to be true at every level all the way down. But there are levels where it does seem to break down. And so the philosopher of science, Karl Popper, really hated this. The one who came up with the idea of the scientific revolution, that there's a new idea that doesn't match the old ideas and then sort of gets moved forward. He was fighting against the earlier, the logical positivists who came up with the scientific method. The idea that you hypothesize, you test it, and you come up with something, a new thing. That became questioned as a process, and so philosophers were trying to come up with new ways to think about how knowledge moves forward. And one of the things that Popper really disliked was the idea of the cosmological principle, the idea that there was anything you saw in the universe must be just like it is here. There's no reason for that. That's essentially a religious statement.
Right. How would you know?
How would you know?
Right.
Exactly. And so he really disliked this. And Newton wouldn't have disagreed with him. He's like, yes, that's a religious statement. And that's what I am doing when I am doing my math and inventing physics.
Proving my religion. Yes,
Exactly. Yeah.
yes.
Yeah.
What a beautiful thing to be able to prove your religion.
Yeah. He didn't see any problem with that at all.
Yeah.
Because it was his math, and he was inventing better and better math that could describe curves and things that didn't add up nicely in 2 + 2. That were infinitesimal pieces of things, right? You can only make a curve out of infinitesimally small straight lines, and he was coming up with a calculus that would allow you to do that, to deal with some of these infinities.
Yeah.
And this was what the Greeks were doing with their mystical things. The Pythagoreans were the early cosmologists, and they were dealing with things like the square root of 2 and pi, which are also infinite series in math, that you're getting closer and closer to something that you never quite reach. But the more numbers in pi you get, the better a circle you've made. So all of these things were not just math ideas; they were also philosophical concepts of how we approach the infinite. And these were people who were thinking really, really strongly about them. When Galileo was observing the Galilean moons and supporting the work of Copernicus, who predicted that there were orbits and that the Earth was going around the sun and not vice versa. Galileo then supported that with observations and was forced...
This is the moons of Jupiter?
Moons of Jupiter. Mm-hmm. He saw the Galilean moons, saw them going around, and said, here we have something orbiting around something, so other things might be orbiting. The moon might be orbiting around us, and we might be orbiting around the sun. Mm-hmm.
But he was the first to see that and be able to prove that these things were actually orbiting another planet.
Right. And so he was
orbiting the sun.
And so he was using the cosmological principle. If he saw this as another piece, then all the pieces could be working like this. And he was before Newton, so they didn't understand gravity completely, but they knew that there was an attraction to the Earth. Things were in some mystical way attracted to each other. They didn't know exactly how it was working, but they could empirically predict it using their math to describe what they were seeing and relate the predictions to what they were seeing and come up with something. But it was still based on this idea of the universe must be the same everywhere, and that we can see small things and then expand it to a larger concept of the universe.
Which is the cosmological principle.
Is the cosmological principle. So this is something that really is fundamental to the way science works, even if it sometimes breaks down. And so this is why everyone wants to have the grand unifying theory that brings quantum mechanics into the Newtonian world, because then you would have something that scaled all the way up and all the way down, and it would be really appealing. And it's something we really, really want. We haven't gotten there yet, but the cosmological principle says it must be true. And eventually we will get there. It might not be true.
It might not be true.
It might not be true. And that's what Popper is warning us about, that it might not be true. And he really hated it.
It might be chaos ahead.
It might be all chaos all the way down. Yeah, exactly. But most good science has been made by people who thought along these lines. A lot of philosophers have said it's really no different from a religious point of view.
Well, I mean, I completely agree, but the opposite is possibly insanity.
Insanity, exactly.
You can't conceive of any of it.
So it's a very appealing sort of branch of very theoretical religion. When Bertrand Russell was thinking about the cosmological principle, he specifically mentioned the Orphic egg, the egg with the snakes wrapped around it, and said that this is the origin of all philosophy, and that any philosopher or scientist with any touch of religion, this is what they were talking about. That this is the origin of basically all of Western philosophy and science up until this time. And this is what Bertrand Russell was working on.
The cosmological principle.
He was trying to, on a pure mathematics sense, be able to derive all math from nothing. And Gödel's the one who showed that he was wrong. So there is also a problem with this, that you can't... What Gödel showed is that you can't have a self...
Who showed?
Gödel.
Okay.
G-O with an umlaut over it. Gödel showed that there are no systems that can be purely self-explained without reference to outside the system. So, you can have Euclidean geometry based on parallel lines not meeting, but you can't prove it within Euclidean geometry. So you can have large scientific or philosophical or mathematical concepts that work and are empirically useful, that are not provable within themselves. And so that's what Gödel showed. And so that's a real problem with this idea of the Orphic egg, everything being contained. There must be something outside even a mathematical system.
So saying that even the concept that math has to be, it's either right or wrong, isn't exactly correct.
Well,
that it can be fuzzy.
It's just that you can't prove it within a given system. You must have recourse to a postulate outside the system. So you have to say something like parallel lines never meet, just trust me. Trust me on this. So there eventually is some sort of foundational faith, even if that faith is not God. It's outside the system. Mm-hmm. And so this is what everything runs into. This is why people like Bertrand Russell say, well, this is religion. The idea of a cosmological principle at its foundation has something that is just a matter of belief. That it's all turtles all the way down has to be a matter of belief, because you can't prove that.
You can't get all the way down.
You can't get all the way down. Exactly. Yeah. But it's a really useful belief. You can come up with figuring out how the universe works by looking at pieces of the universe. And this is what all of science is based on.
Lots of really good images of turtles.
Yeah, exactly. Yeah. So this is not a cult type belief. This is a belief that the world must work this way, but we can't ever prove that it really does work this way. It's just, we know it has to, because otherwise the world doesn't work. As you say, insanity.
Right.
It's chaos and insanity otherwise. And this can only be based on a certain kind of faith, but not the kind of faith where you'd say, well, the world's 12,000 years old and I don't care about dinosaur fossils, right? It's not that kind of faith. It's a more rigorous approach to understanding that everything must have some sort of foundation. The turtles have to stand on something.
Right. Even if we can't see it or prove it.
It has to be because there's a something.
Yeah.
And so this idea is really seen through human history, human thought. It's something we've been working on for a long time. It's where monotheistic ideas come from. It's where Pythagorean and Neoplatonic ideas come from. It's where a lot of the alchemists were coming from. It's certainly where Newton was coming from. And it's where, many of the 20th and 19th century philosophers, what their ideas were, Hegel, Kant, etc. All of this is working from this same point of view. So when I was an undergraduate, mm-hmm. I was reading someone called Nicholas Koussanis. I was studying with a woman named Pauline Watts, who was a brilliant scholar. She translated him. She'd worked with her husband, Charles Trinkus, and they were, really the tops of the of the Renaissance scholarship field. And I thought this was an interesting guy. He had lots of pictures of circles, and he was trying to get at Neoplatonic concepts. But I didn't really understand, why something like this would be all that exciting. It was just something I was reading as an undergraduate, and I was reading with this great scholar who was fun to work with. And it's really, really great to work with, the author of the book you're reading, who's the top in her field in the world. And, I found that terribly exciting. And, there's 10 other students in the class with me, and,
it's amazing.
Sitting right next to her as she sits there and pulls on her rubber bands. Like she would just stare directly at the rubber bands and pull them the entire time. It was great. As
she had to have what is now called a fidget.
Absolutely. Yeah. There's in academia, there's a lot of the non-neurotypicals out there. We often don't fit in the rest of society very well. So we tend to do things like that. So anyway, I had a lovely time with her. And I had some ideas that had grown out of that class, but I didn't worry about them too much because, as an undergraduate, you don't really think you have real ideas. There's sort of things that everyone knows because you just read them. Like everyone knows these things. And later in life, I was reading histories of science because I was interested. And reading about people like Giordano Bruno. He's the theologian who said Galileo was right. listening to the pigeons outside.
Yes,
I'm hoping not they're getting picked up with the mic too much.
I think we can just move.
So Giordano Bruno saw the work of Copernicus and Galileo and said, there must be a cosmological principle. It's not just the Earth goes around the sun. Those stars out there, those are also suns, and they must also have Earths going around them. And if something is true here, and we had Jesus coming to bring us the gospel, then there must be Jesuses on all of these worlds.
This follows the cosmological principle.
Exactly. And so he saw clearly. He's often depicted as that guy with his head sticking out through the sphere of fixed. So in the Middle Ages, we thought there was a sphere of fixed stars, and that they twirled around the Earth, right? So
why not?
Yeah. So there's this outer, and so it's like a dome. For the Earth is hollow, and I have touched the sky.
I love it.
Yeah. So Giordano Bruno was that guy. He stuck his head out through this sphere of six stars and saw the universe as a whole. And so you see him in these medieval things where they're making fun of him as this foolish philosopher who's stuck his head stuck through the sphere. He saw that there must be an infinite universe. And it was actually partially due to the work of Pauline Watts that it was understood that he wasn't actually the first who saw there being an infinite universe. It was actually Nicholas Cusanus. And what Nicholas Cusanus had said was he was trying to come up with metaphors for what God is. And what Nicholas Cusanus had said is the universe is a circle whose center is equal to its circumference. And so the only way you can have a circle whose center is equal to its circumference, well, there's two ways. You can have a non-dimensionist point, a point with no dimensions. The circumference is the same as the center because they're no distance from each other. They are the same thing, right? A point. So that's one way you can have a circle whose center is equal to its circumference. And the other way is with infinity. In an infinite circle, an infinitely sized circle, everywhere in the circle is the center and the circumference because there is no edge. It goes in all directions.
Breaking my head a little, but I get it. I get the idea.
If you're standing in a spot, it's an infinite direction.
Anywhere you are, if you look, it's infinite. So therefore, you're in the middle.
You're in the middle. Exactly.
It's the same in all directions.
But if you pick any one direction, you pick a spot. That spot could also be the circumference. Because it's
infinite.
It's infinite. Exactly. And so this was a concept he'd come up with. Giordano Bruno did read Nicholas Cusanus, so he knew about this. And so they were coming up with the idea of the universe is infinite. And it's the same as what we see here everywhere for infinite directions. And so he was taking the cosmological principle.
That's pretty boring.
Well, somewhat boring, but he got burnt at the stake for it because it meant there was no heaven and hell below us and above us. And, we weren't the center of everything. And so there was multiple Jesuses and all this kind of stuff that you can't have.
Nope.
So they literally burned him at the stake for this when he lost his patrons, and so he was no longer supported, and he kept insisting that everyone else was an idiot because they couldn't see this stuff that he could see. Exactly what Plato was talking about in the parable of the cave, the myth of the cave in Plato's Republic. The idea of the philosopher realizing that these are just shadows on the wall that we're seeing, and he sees reality, is likely to get burned at the stake by the people who see the shadows because he's coming in and telling him we're all wrong, and they're able to predict the shadows better than he is because he's concentrating on the actual source of light outside the cave. And in the allegory of the cave, they actually say, no, the people in the cave will be able to predict their universe better because they're seeing shadows that they've been watching their whole lives better than the guy who can go out and see the sun.
Therefore, the guy who goes out and sees the sun seems insane.
And gets burned at the stake. So that he's the one who sees through the sphere of six fixed stars. He's Giordano Bruno. And so this has been something that's been happening for a long time, that we get blinded by our own immediate world, and we stop thinking about the cosmological principle and seeing a wider world. And every time someone succeeds in understanding how our world relates to the universe outside there, we get a better understanding of the universe. And it has happened over and over again. And often the person seeing these things is ridiculed. So while I was undergraduate thinking about Nicholas Cusanus, and he had his picture of a dot being the same as circumference, and talks about it, and he had all these things that were part of his philosophy and predicting an infinite universe. I was talking to Pauline, and she was saying how there were a lot of researchers in Germany, and the physicists were really excited about this because it was an early prediction of how the universe would have to be, and then the universe would have to be a circle whose center is equal to its circumference, which is really interesting to think about because the modern conception of the universe is no longer truly infinite. We started at a particular time. The universe has a beginning. Something that has a beginning is not truly infinite. It didn't go for all time.
True, but we don't experience time backwards. We experience time moving forward.
So we have infinite
believe it's
forward.
Infinite. Yes.
Right. So time is infinite in forward, but it is finite in the reverse.
Or so we believe, yes.
There's other aspects of the universe that are not infinite. The speed of light is fixed, and it is a fixed absolute. So there's a couple of fixed absolute points in the universe. One is the beginning, and the other is the speed of light. And so these are things, Einstein used the idea of a fixed point to come up with all of his physics. These are things you can use as sort of a leverage to come up with a concept of how the universe must work once you have these fixed points. And so I really, for the last 30 years plus, have been thinking about this idea of a finite yet infinite universe that's both bounded with ligatures of strong necessity, but also infinite in the sense of there's no real end to it in any direction ever, but it's still in some way bounded. And when you look at modern cosmology from the Big Bang, there's hints of this. One of the big hints of this is the cosmic background microwave radiation is the same in all directions. This implies, and it should be the same in all directions anywhere you are in the universe. And so this implies a cosmological principle that anywhere you are in the universe, you would see the same thing on average looking out in any direction.
Any direction you looked from any point in the universe,
you would see the same thing.
You would see the same thing.
And what that thing is it represents the Big Bang itself. It's the beginning. And so the beginning is in all directions.
If you're looking out, you're looking back.
You're looking back, exactly.
Any out is back, and look back far enough, you hit the Big Bang.
You hit the Big Bang, and the Big Bang released its radiation as it got big enough, as it expanded, right? The universe is expanding. As the universe expands, there's a point when light can start escaping, right? So light was just going, I don't even know if you can talk about them as particles. This is way outside my realm, cosmological physics, high energy stuff.
Prior to expansion, I don't know if photons were differentiated.
They weren't, right. So at a certain point, you get far enough, things are far enough apart that they're things.
Yeah.
And the photons that were just bouncing back and forth between them now can start spreading out. And they're now spreading out in this expanding universe. And we're still seeing those photons expanding. And that's the microwaves. So those microwaves are photons that over a very long period of time have gone down and down in frequency until they're now very long wavelength microwaves. And they are the remnants of this Big Bang as it got big enough that the photons could actually escape.
That's the earliest photons?
Those are the earliest photons, yes.
That existed at the Big Bang. That's the background radiation.
Sometime after the Big Bang.
Sometime after.
Yes, but they existed in all directions from the beginning. And we see them in all directions from anywhere. So where did they escape to? Where did these photons escape to? They escaped to the universe, from the universe.
Everywhere.
From the universe to the universe.
Everywhere.
To everywhere, from everywhere.
Right.
And so this has become a fundamental idea of the nature of the universe, is that it is the same everywhere, and that it had the same energy in all directions from the beginning. And so this is a sort of the standard model for the universe beginning, is that this sort of energetic signature was essentially homogeneous. It was isotopic in the sense of same in all places. Mm-hmm. Isotopos, all spots.
Except for the tiny little pockets which created...
Okay, so we think that there were actually fluctuations in, quantum
density,
froth, essentially.
Right, exactly. Density of quantum froth, yeah.
Yeah, so the weird parts of the quantum world are that you can't ever have anything that is exact. Things are more or less. And so more means you get a planet, less means you have interstellar space.
More means you get a galaxy. Less means you have interstellar space. Yeah.
And so all of these things are started by the original quantum fluctuations pulling pieces of matter together so that they can then coalesce. But again, even at this level, you're seeing quantum fluctuations writ large. You can see patterns in the cosmic background microwave radiation that match what would have been a quantum effect when it was that size. Mm-hmm. When things were small enough, you would have gotten these quantum fluctuations, which would then show up writ large, 13.7 billion years later.
Mind-boggling.
So what I was thinking about when I was reading Cusanus was the nature of light itself and looking back in time. And so I don't just see the background microwave radiation, I see the Big Bang. I see the beginning in all directions. So I am standing at the center of the universe with the Big Bang everywhere in a circle around me. Mm-hmm. Anywhere you stand in the universe, this must be true because everywhere in the universe is the same age. This is not a wacky concept, right? Everywhere the universe starts at a certain age,
right?
Then it must be a certain age.
You're saying not that we know that the Earth is a certain age or we know that a galaxy is a certain age. You're saying that the universe itself, everything that exists, wherever it came from, started at the same moment. Right.
And so therefore must have the same age.
Right.
And would look the same from anywhere from that point of view, that you would see the same energy, the same background radiation everywhere. And people have largely accepted that. Mm-hmm. Even the ones who don't like cosmological principles are like, okay, fine for this context. Probably. But maybe it's different somewhere else. Maybe you'd be outside the universe. I'm like, stop it. I don't know what you're talking about. What would that even mean? But the idea that it's the same everywhere is fairly well accepted. But it has to be the same everywhere in terms of time as well, so that the beginning is in all directions around us. So everywhere in the universe is the center of the universe. If you were one of those photons starting at the Big Bang,
or just after the Big Bang,
and you're moving in a straight line to my telescope or receiver or eye. My eye is seeing this light. It's too long a wavelength to see as such, but some detector is detecting it. That light has now been moving for, let's say, 13.7 billion years in more or less a straight line outward from the center. So the place that's seeing it 13.7 billion years later is the edge. You can't be farther than that. There is no place in the universe that can be farther away from the center than 13.7 billion years from the center.
And everything is that far from the center.
Everything is that far from the center. So that everywhere in the universe is the center, and everywhere in the universe is the edge.
Is also the edge.
So we are indeed in a circle whose circumference, or in a sphere, whose circumference is equal to its center. However, it's not quite the one that Cusanus was envisioning. He was envisioning an infinitely large circle where there would be no drawable edge. But here we're talking about something where there's both a beginning and not exactly an end, but a point we've gotten to now. Mm-hmm. There's a now that is a straight line between the beginning and the now. And that now is the same distance from the beginning in all directions.
And we say that we have proven that everything is expanding, moving away from each other, which is exactly what this would say.
This is essentially what this would say, indeed, yes. And so it's all expanding away from a center for the same distance, which is 13.7 billion years.
Except the center is...
everywhere.
Everywhere. And
yes.
The edge is
everywhere.
Everywhere.
Yeah, so it's difficult to conceptualize. So this is something that behaves like infinity in many ways, and yet has a finite term to it. I had thought this was well understood because I'd thought about it when I was like 20.
Well understood.
Well, because it seems so obvious.
Somebody said this to you when you were 20, so you said, well, of course.
It makes sense. And a guy from the 13th century said this to me when I was 20. Mm-hmm. So I'm like, sure, we know this.
Yeah.
We definitely know this.
So where did you walk around proclaiming this as if everyone knew it and get caught?
Well, no, I would say it randomly to mathematicians and they'd be like, yeah, that sounds right. But like not think anything of it because it seems so simple to them and me. Uh-huh. And I would say it to a physicist and they would sort of frown their brows, turn their head and say, there must be something wrong with what you're saying. Or I'd say it to them and they wouldn't understand what I was trying to say. And they'd be like, well, there is the cosmic background microwave radiation. I'm like, yes. But think about that. That's energetically uniform, but we are positionally uniform. Mm-hmm. So not only was the universe all one temperature at the beginning, everywhere in the universe was in the same spot at the beginning, relative to the universe.
Did you say that to somebody who initially disagreed with you?
I've been trying to figure out ways to say this better now for 30 some years, so that I can talk to a physicist and they'll start to get what I'm getting at. Mm-hmm. And when I've actually read cosmological stuff, and they get the energetically, it has to be the same everywhere. Mm-hmm. But no one mentions positionally because it really seems like different places are in different spots.
It really seems that way.
It really does seem that way.
I mean, when I go from one place
from
to
here
another,
to there, it seems like I have moved.
And the language itself tells me that I was here and now I'm there.
And so this is the problem.
But the thing is that when you're there, you don't call it there, you call it here.
Yeah,
it's
exactly.
always here wherever you are.
And wherever you are is the same distance to the beginning of time. Everywhere. And so this is the problem that Parmenides was having. This is why the Heracletians, the people who believed in many instead of one, said that you Parmenideans are crazy because if there's only one, I could never go from here to there. There would only ever be one. And then Zeno criticized them. Zeno was a follower of Parmenides and said, well, if there's many, you can never go anywhere either because you only go halfway and then halfway and then halfway.
He's the one who said
that's Zeno's paradox. You'll never get there.
Yes.
You'll never, ever get there. So as soon as you start dealing with these kinds of things, things break down.
Very quickly.
Very quickly. But the cool thing about modern science is you can actually look at things and observe background microwave radiation and say, look, it's the same in all directions everywhere. We can come up with, oh yeah, the universe is expanding from a point. So there was this huge argument between sort of the Old Testament, New Testament people who thought the universe started at the beginning and some of the Greeks who thought it existed forever with no beginning. And it turns out there's an answer. There was a beginning and it started and progressed from this starting point. And so these are things that you can make a prediction and actually look at it. And so that's, why we now have a scientific way to think about what had always been merely concepts. And as science has progressed, there's been arguments between, Galileo and the church, because he thought of the cosmological principle saying, here's how the universe must be. And the church said, no, this is what the book says it must be. And so there was a disagreement. And eventually the church gave in because the universe has to be the way the universe is. And so I've been feeling this way now for some time about the idea of the universe being a bounded infinite, of everywhere has to be the same distance. And it really has to do with the speed of light. And the universe is 13.7 billion light years in all directions. As you get closer to the edge, weird stuff starts to happen. As you see the first galaxies, they get bigger and bigger and bigger. Why are they getting bigger and bigger? Because they're everything. They're becoming a larger proportion of everything, because at the very beginning, it's everything. At the very beginning, it's this one point, and that one point is spread equally in all directions around us. That's the microwave radiation. That one point of the Big Bang is the outside of the shell we are living in. That is the beginning of time in all directions. And it looks the same in every direction, but it started out as a point, and that point has now been spread everywhere in all directions equally. Galaxies start to do this. As you look backwards in time, they get bigger and bigger and bigger because they're becoming closer to that original point that was smaller and space itself has expanded. And so the things from this time look larger.
Giant.
They have a bigger portion of, if you could see the very beginning, you would see it the same equally everywhere. And that's what we see.
It would just be a dot. It would be a bright...
It would be a smear.
It would just be a smear of white everywhere, light everywhere, just
that's
photons everywhere.
And that's what the microwave background radiation is. It's a smear of
smear of photons everywhere.
Yeah, exactly. So this is we can make a prediction, and we see this. You say you look far enough back in time, things will start getting bigger.
As much as I love and adore this, and I've loved and adored this all of my life and all of our lives, it's still a little overwhelming. It's
a little overwhelming, and it makes you start to think about things that don't work. Like, you think of the universe as a balloon that's expanding, but the universe isn't a balloon. We're not on a surface, and it's not expanding in something. The universe is expanding itself.
We have to be on a surface the same way that we experience the surface, like the air, or the atmosphere around the Earth, as just this giant three-dimensional space, which really is this very, very, very narrow band. It's got to be. But then it begs the question: what's on the outside of that? There's nothing.
So the surface that we're standing on in that concept,
would
be time itself. The present moment is the surface we're standing on. So there is no outside of, because that's the future, and there is a before, right? There is a past. And we can see the past. When we look back in time, when we look out there, you're looking back in time. Mm-hmm. So inside exists, but outside doesn't exist for the simple fact that it's the future.
It hasn't been made yet.
It doesn't exist yet. It is literally the future. So I thought that this was well understood. Everyone got this. And this was exactly what everyone was talking about when they talked about the Big Bang. And that their people's metaphors were having difficulties because it was just really difficult to imagine dimensions that there's no more than 3 dimensions of space plus 1 of time. Mm-hmm. But that leaves no dimensions for this to be expanding in. Mm-hmm. So that means there's more dimensions? No, I'm not adding any dimensions. The only thing we're talking about is expansion in 3 dimensions through time. Mm-hmm. I'm not calling for anything extra.
So you thought everyone understood this?
Yeah, but it seems like when I start saying it seems like I'm talking about a curved universe.
Yes.
I'm not talking about a curved universe. Everything is straight. A curved universe needs another dimension to curve in, right? If I have a, I can make infinity.
Well, but if you're talking, if the Big Bang started, if it was a point, and then that expanded out, it expands in all directions.
Right. So let's think about when space really does curve. So I've got a gravity well, like a black hole, and it's curving space. The only way I can conceive about that is I can make a 3-dimensional model of curved space, but the curve has to be happening in a 4th dimension.
Right, exactly. Because space itself is curved, and then you think of it as curved.
Because you start off with a flat plane of space, and then you curve it into the 3rd dimension. But the model is a 3-dimensional space that's actually being curved into a 4th dimension. I don't worry about that. Yeah, that's not what we're talking about.
Well past anything.
That is definitely not what I'm talking about. And people are now starting to think, well, I'm going to try and get there. People are now starting to think that space is not curved, it's flat. So I'm talking about a flat universe that is both infinite and bounded. It's infinite in that...
Well, how can space be flat if it's clearly 3-dimensional?
It's... All right, we want to go there now. I was going to go there a little later, but
I'm sorry. Let's go back to your track. Forgive me.
I was almost there.
Okay. Forgive me.
Okay. So the universe is beginning at a time, and we exist at a time that is later than this beginning.
Yes. Later than its beginning.
Yes.
We are after the beginning.
And we see the beginning in all directions because time has progressed the same equally everywhere. Again, this means that positionally, everywhere in the universe would be the same in terms of how it would see the universe.
Its relationship to the mid-center.
There's no place you can go in the universe where you could see a universe that was older than 3.7 billion years old, because the universe began at a time. Mm-hmm. It can't be older than that. So it doesn't matter where you go, you would see the same thing in those terms. This is contradicted by Google. And I think Google is wrong, because for me, the cosmological principle must rule. So that if you look up, try it as a listener, not you, Eric, as a listener, try it.
But still, yes.
Okay, Eric is now trying this. You can hear his mouse clicking. And and ask a question like, can the universe move faster than the speed of light? Or another question, how big is the universe?
I want to do that one. How big is the universe?
Either one of these questions, in my opinion, comes up with the wrong answer. And this means that these are well understood wrong answers that everyone in physics would support and that I am now contradicting. And I find this to be maddening.
Yeah, I think part of the reason I'm sighing is because we may have discussed this before. I don't understand how the universe is 93 billion light years.
Exactly.
That's what it says.
Exactly. So let me tell you what Google is saying. 0.7 because it has a beginning. Okay, so let me tell you what Google says. What Google says is that yes, we can see, let's say I can see 13 billion light years. So I see 13 billion light years in one direction, and I see a star. I see 13 billion light years in another direction, and I see a star. These two stars are therefore 26 billion light years away from each other.
Where do you get to 93?
Now, in the course of the age of the universe, these stars have been expanding, right? The universe itself has been expanding. The rate of expansion can be measured by the distance of any two things. The further something away is, the faster the more redshifted it is. So this is well understood physics. Something's further away, you can actually calculate distances by its redshift. In an expanding universe, when things are moving away from you, because of the Doppler effect, the wavelengths are further apart, so they move closer to the red end of the spectrum. Mm-hmm. And so this is, the red shift, and it shows ages of things. Something that's more red is older. So these two stars that you've now calculated are 23 billion light years away from each other, even though they're only 13 billion light years away from you, during the course of the universe have been expanding. And because they're now 23 billion light years away from each other, and there's a formula that tells you how fast the universe is expanding, and you've now plugged in the 23 billion light years into the distance between two things, and you're looking at the expansion rate, it turns out that these two stars have been moving away from each other at faster than the speed of light. Because they're that far apart. And because
But then how do we even see them? Like, I don't understand. I'm so confused.
Only relative to each other, right? They'd be moving faster away from each other, faster than the speed of light relative to each other, because the universe is expanding.
Relative to each other.
And because the universe itself is expanding, it doesn't violate the going faster than the speed of light. Now, each of these stars can see another star. And that star is another distance away from each other. And that's also been expanding. So they add all these things together, and they come up with a number of, because of this, the things we can see in both directions, the total size of the universe is 93 billion light years apart.
Well, Bing is actually saying that this is only the observable universe. The entire universe might be 250 times larger, saying that it's at least 7 trillion light years across.
Yeah, so anyway, so these things are based on things moving faster than the speed of light, and they're based on an idea of not everything is how we see it. It's going against the cosmological principle, in my opinion. And it's breaking some rules. Because these stars are not 23 billion light years away from each other. They're only 13.7 billion light years away from each other. And it doesn't matter if I see one 13 billion light years in one direction and another 13 billion light years in the other direction. Because if I'm standing on one of those stars, how far can I see? I can only see 13.7 billion light years. And so Earth is only going to be 0.7 billion light years away from the very beginning if I'm looking at something that's 13 billion light years away. So if I'm looking 13 billion light years. Mm-hmm. I'm standing on another star or planet that's 13 billion light years away.
From Earth.
From Earth. If I looked at Earth, Earth would only be 0.7 billion light years from the very beginning. At that time, it would have been right next to this other star. Mm-hmm. And so that other star itself can't be more than 13.7 billion light years away, because that's the very beginning. Once you get that far back, you're looking at background microwave radiation. You're looking at a shell of the beginning.
Mm-hmm.
As things go further and further away, they fill more and more of the sky. And so if you're looking at something that's further away than the beginning of the universe, you're looking at something that has filled the sky entirely or is outside of the universe and is older than the universe. And there is nothing older than the universe by definition. To be further away than 13.7 billion light years means you're older than 13.7 billion light years. By definition.
I hear what you're saying because of the way that you led me into this. I'm just amazed that right now, Bing's AI is absolutely accepting that the universe.
Yeah, no, everyone says I am wrong.
7 trillion. There's 7 trillion.
Everyone says I am wrong, and the reason is because the universe has been expanding faster than the speed of light. And that there were periods of expansion that were faster than they are now.
Well, because what's explained in this explanation of the 7 trillion light years of space that there is actually easier to comprehend than some what sounds like gibberish that every spot is both the middle and the edge. Like that's a very difficult thing to wrap your head around.
Right. So let's talk about some modern physics that is a little bit easier to understand, but just as wacky. This is what I was talking about with Einstein and his thought experiments. They come up with a lot of great math, but Einstein didn't start with math. Einstein started with an idea. Some people had done an experiment. So Michelson and Morley did an experiment, and they were looking for the universal ether.
The universal ether.
And the universal ether is what the waves of light moved through. So just like waves move through an ocean, the universal ether is the thing that waves up and down when light moves.
The thing that waves up and down.
Right. So the ocean is what waves up and down. The waves are not the ocean. The waves are the energy moving through the ocean.
Okay.
But the ocean is its own thing that is separate from the waves. And the waves are made of the ocean.
That sounds like some tortured thinking.
Well, it made sense. It's how we understand waves. Have you ever seen a wave of nothing? No, you have to have a wave of something.
Right.
The thing doesn't move. If you take a string and you make wave, you have two people holding ends of a rope, and you're making waves in the rope, traveling from one end to the other. That's exactly how light moves. The rope doesn't move. The energy is contained in the wave, but the wave is made of a rope. So we thought that light was made of a rope, of a universal ether. Mm-hmm. There was this thing that waved up and down, and that's what made light. Mm-hmm. And so Michelson and Morley figured out that the fastest thing that they had on Earth was Earth itself. Earth spinning around the sun was moving faster than anything they could produce in their facility, mm-hmm. and still put a decent detector on it. Mm-hmm. If you try to make something move that fast, it's really hard to have accurate measurements. Whereas if you just use the speed of the Earth itself, you can tie things down really nicely and get really good, accurate measurements.
Just bolt them to the Earth.
Yeah, just bolt them to the Earth.
But use what to measure if the whole Earth is moving?
You use light itself. And so there's what's called interferometry. When you have a wavelength of light and it encounters another wavelength of light, there are places where it cancels itself out, and there's places where it increases itself, just like waves in a pond. When waves in a pond meet, there'll be some waves that go higher and some waves where they disappear. It's just where the down part meets the up part, it disappears. Where two up parts meet each other, it accentuates, right? That's interferometry.
Yeah.
And so once you've calculated these things, you can have two light beams shining at each other that create a pattern where if those things change at all, you'll see differences in that pattern of interference between the two light waves. Mm-hmm. So they calculated that if the Earth is moving in a particular direction through the universal ether, light going in one direction will be slightly faster than light moving in the other direction, because one of them is moving with the direction of the Earth and one of them is moving against the direction of the Earth.
Sure, that seems to make sense.
And if there's there's a universal ether and you're measuring at the distance of the wavelengths of light itself in nanometers, you should be able to figure out, we see a difference, and that would be detecting the universal ether, that there is a difference in speed between light speed plus the Earth and light speed minus the Earth.
Right.
That these two numbers can't be the same.
This should be measurable.
A speed x speed at 1 plus speed 2 must equal a different speed than speed 1 minus speed 2.
When did they do this work?
Like 1920, something like that. Okay. Good work.
Sounds like a great experiment.
Great experiment. And they did not find anything. And they're like, there's something we don't understand.
Yeah.
Light is the same in both directions.
Isn't it interesting? We still don't understand it.
But they just said it. And so Einstein, working in his patent office, was just reading paper and was like, light's the same in both directions. I'm getting goose pimples just thinking about this. What does this mean? It means that two beams of light moving towards each other are not moving at twice the speed of light. They're moving at the speed of light towards each other. Even though it's two beams of light moving each one speed of light plus one speed of light.
In other words, if you are riding one of the light beams, wave, particles, if you're riding one beam of light and you are measuring the speed of the other one coming at you, you'd still get 186,000 miles a second.
Yeah, exactly. So light doesn't matter which way it's going. Doesn't matter if you can boost something up, you can't get past it, you can't go faster than it, and light becomes related to time itself.
It's a speed limit.
It's a speed limit that's related because time is motion across distance measured by time, right? The less time you take to go a certain distance is the faster you're going.
The faster you're going.
Right. So velocity is distance over time.
So light has an absolute
fixed speed,
velocity,
and doesn't matter what you do to it.
Doesn't matter how you look at it.
Exactly. And so this is the world that I am thinking about. I am thinking about a world where the velocity of light is indeed fixed, even if you have an expanding universe. If the universe has expanded somehow faster than light, you wouldn't be able to see it for sure.
Right, it would be gone.
But it would also be moving backwards in time. The reason it would be gone is it would now be before the Big Bang.
Because we can't see past the Big Bang. We
can't see past the beginning because we're seeing backwards in time via light. And light can only move at one speed. And so if you go faster than that speed, this is why time travel and all these things are related to the idea of relativity. Light itself does not experience time. Because if you have two light beams moving towards each other, each moving at the speed of light, and 2 times the speed of light is the speed of light, that means that one of those light beams is stopped, and the other one is moving at the speed of light.
Which we know is not true.
But it's exactly the same as what's happening.
I once read this fascinating account that if a photon were created in a star and you were that photon, from the moment you were created and eventually ejected out of that star, flying hundreds of thousands, millions or billions of light years until you reached someone's eye and went in, the moment that you were created and the moment you went into the person's eye were the same.
Yeah, essentially,
to
because
the photon.
Light is completely reversible. It has no.
But I think it's more of what you said is that it doesn't even experience time.
It doesn't experience time, and that's part of what makes it reversible. And so, for all of these things to be true, I think we must live in the universe that I am describing, and not the one that Google is describing. That we live in a bounded universe that is both infinite and finite. It has a finite beginning. It has an infinite directional future, outward, expanding into the future, because the future has no end point. And I also think it is flat. That's what we were talking about before, that you were asking how can something that's three-dimensional be flat? So it's flat in the sense of there's different ways you can conceive about the universe. If there's enough mass in the universe, eventually it will expand to a point. If you think of expansion as positive energy, throwing everything apart, gravity is negative energy, pulling everything back together again. If the positive energy is exceeded by the negative energy, eventually the universe will come back together again and form a new black hole beginning. And so some people think it goes that way.
If the positive energy is exceeded
by the negative energy,
wouldn't it?
Eventually everything will crush back in again. It's called the big crunch.
But doesn't the negative energy have to exceed the positive energy for that to happen?
Yes. Yeah. So negative energy is gravity. So if gravity exceeds the expansion of the universe,
right?
So the expansion of the universe
would eventually slow down,
is
and
what
pull
people
everything back.
call dark energy.
Right.
It's the energy that throws everything apart.
Mm-hmm.
So gravity could exceed that, and the universe would collapse again. Another possibility is there's more positive energy, the dark energy, than there is gravity. Then the universe keeps expanding forever and never gets pulled back.
It's a very sad and lonely concept.
The people who measure dark matter think that there's so much dark matter out there that it seems to be perfectly matching the dark energy. So the energy pushing us apart seems to exactly balance the amount of energy pulling us back in.
So then why would we be moving at all?
Well,
something has to be out of balance there.
That's the thing. That's why I said the universe is zero. The universe is all of it's infinite negative and infinite positive. It's the universe is expanding, but in a not curved way. Matter curves the universe, and basically, if you can think of the curve happening outside of our three dimensions, right? So matter curves the universe in one direction, and dark energy curves it in the other direction.
Therefore, it's flat.
And therefore, it's flat because there is no curve.
So the Big Bang, instead of is conceiving of it as an explosion moving out in 360 degrees like a balloon or a ball, it kind of spat everything out flat. And
that flat is indeed a ball. That flat is a sphere, but it's a flat sphere in terms of it's neither positively nor negatively curved over space-time in that sense.
Having a hard time conceptualizing
but itself is a sphere bounded by time itself. So the edge of the sphere is the beginning of time, and there is no outside that sphere. And the beginning of time is 13.7 billion.
I hope I don't know why. I hope that you're right, and it's a very appealing concept. The thing is that you have quite an uphill battle to get the word out against Google.
I know. I'm doomed. I'm absolutely doomed. I really hope someone listens to this podcast. Part of why I've done this podcast doesn't have a lot of human evolution in it. Every other thing I've done, I've at least mentioned human evolution. There has been some cultural evolution discussion. We've definitely mentioned culture, the buildup of this idea, where this idea comes from, historically, how it fits into a larger narrative. I've done that. But the reason I've done this podcast is I would like to be able to send an email with an attachment and say, I didn't write a paper, but here's my idea.
Well, I
don't think anyone will ever listen to me. Not anyone important.
Well,
but I'm trying.
Hey, guys, there is a transcript of this, and
that's true. Someone could read it.
www.mindbodyevolution.info is the website, and you can read it all there. But yeah, you have quite a battle, especially when even the AIs are collating this information and saying, no, it's 73 billion light years across.
So I just wanted to mention this as a hobby of mine, is finding disciplines in which I know nothing and coming up with ideas that contradict the entire discipline. And it's a hobby of mine that I really enjoy. But it's somewhat of a doomed hobby.
Well, for this one, it sounds like you should sit down and try to write a book, because if nothing else, to piss people off and get people talking, because it sounds like there's something to it from the nothing that I know. Anyway, fascinating. Thank you, Josh.
Well, thank you.
All right. Until next time.
Until next time.